Hi, today we're going to be talking about section 3.4 from your books, velocity and other rates of change. We'll be talking about instantaneous rates of change again. We'll be talking about motion along a line. We'll be talking about derivatives in economics, marginal cost and marginal revenue. We need to go through a few definitions before we can really start working some problems and see if we can understand what these different rates of change are. So an instantaneous rate of change, we've talked about this before, is just given by, one of the ways you can do it is at A, f prime of A, so the instantaneous rate of change is equal to the limit as h goes to 0 of the function f of a plus h minus f of a all over h. So that's kind of been our standard rate of change that we've been working with. The average velocity comes from displacement, or the change in your position, which the book uses position as s, so change in s, over the time traveled, or travel time, the change in t, which is equal to f of t plus the change in t minus f of t all over that delta t. So thinking about that, then instantaneous rate of change, or also known as velocity, could just be described this way, where it's just the v of t is equal to ds over dt. So kind of another way to look at it. So the velocity is just the change in position, with position being s. So don't confuse that with speed. Here's another definition for speed. Velocity would mean I'm heading north at this speed, and then I'm heading south at this speed, kind of just those two dimensions there. Speed would just be the absolute value. Speed doesn't care if you're going north or south. Speed just cares how fast you're going. So that would be the definition of speed as you see there. Acceleration, any of these rates of change, all, like when we're talking about the change in velocity, what you're really, or sorry, when you're talking about velocity, you're really asking yourself, what is the change in position? So that's why it's the rate of change of your position. With acceleration, all it's asking is how fast is the velocity changing. So acceleration is just the derivative of the velocity function. So the derivative of position is velocity, the derivative of velocity is acceleration. The second derivative of the second derivative of position is acceleration. So that's kind of all described here. Excuse me. Again, before we start answering some of these questions, we just need to know some units for free fall. English units would be in feet per second squared, so gravity is 32 feet per second squared. The equation for that change in position is 1/2 acceleration, which is 32 times time squared, which simplifies to 16 t squared. The metric units is 9.8 meters per second squared. Sometimes you'll see it written as 9.81 meters per second squared. So if you're representing the position equals 1/2 times 9.8 times t squared, which simplifies to 4.9 t squared. So that is using gravity as your acceleration there on a free fall. Okay, so let's talk about particle motion. And this is a really good problem. I like this a lot from your book. So we're going to do it because you guys won't do it, because you don't get to those problems. The position or the x-coordinate of a particle moving on a line y equals 2 is given by x of t equals 2 times t cubed minus 13t squared plus 22t minus 5, where t is in time per second. So this is, again, the position of a particle moving on the line y equals 2. So this is a parametric equation. It's just a simple one with y values staying at a height basically of 2. So we're just talking about this thing moving horizontally, and it moves with that equation. So describe the motion of the particle for t is greater than or equal to 0. If I graph the function, here's what the graph of this looks like. We were looking at it for greater than 0, so if we were describing this, we would say that if this is a position function, x is moving closer to us until it hits this point where it's right at us, and then it goes farther away from us, above us, and then it gets closer to us until it's right at us here again, and then it's farther away, and then it gets closer until it's right at us, and then it gets farther and farther and farther and farther away. So you just have to say the difference between, you could say it's to the right or to the left of us, you could say it's up or down. Since it's x, you'd really probably say this is left, since it's negative until here, then it's right of us, then it's left, now it's right. So that's probably how you would think of it instead of up and down. When does the particle speed up, or when does it slow down? So if we're trying to find that, it would help to look at the velocity curve. So if we looked at that, we would just take the derivative. So the derivative of this is, using the power rules, we go 3 times 2 is 6. T, the power goes down to 2, minus 2 times 13 is 26. T, power goes down 1 there again, plus 22. So if I was to graph that, it would look like this red function here. And sorry, the bottom kind of got cut off. But you can see, remember that the this is the velocity, v of t. For looking at the position here, velocity is just the slope of the position. You can look at, that's pretty steep. Alright, it's steep, 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 and then not until it gets about here does it really start slowing down, and then we hit a slope of 0. So you can see that 0 slope matches up with that 0 velocity there, and then it's going to go down into the negatives until it hits 0 again. Notice 0 and 0. The slope of the blue line is 0, so the slope function or the velocity is 0, and then it's back up again. So the particle is slowing down all the way from, if you're looking at this, you're starting at a steep slope up until this point where it finally hits 0. So that whole time the particle is slowing down. Alright, then it's going to speed up until it hits about halfway between these two again, and that would be right where this value here is. Okay, it's going to be speeding up to that point. When you hit there, the velocity will change and get smaller and smaller again. So about that halfway point, again, it would be at the bottom of this. Sorry, it didn't show up. Until it goes up to 0 there. So there it slows down to 0, and it speeds up again from then on. So when does the particle speed up? Well, the particle speeds up from, if I was just going to estimate these points, I would say that that point there, alright, is that point. So I would say it's slowing down, I guess, during that part. So slow from, let's see, 0 is less than x is less than or equal to, maybe we'll call that like 1.2. Okay, so that would be that first part that it's slowing down, then it speeds up till it hits about this point, which is the bottom of the parabola here. I'll say that's 2 seconds. I'm kind of estimating. So then it slows down again from 2 less than x less than or equal to up until it hits, I would say that mark, which is this 0 mark here. So we'll say that's at 3.2, and then it speeds up during the other time. So slow during that, slow down, speed up from 1.2 less than x less than or equal to 2, and then x greater than 3.2 would be when it speeds up. So that's how I would describe that motion there. When does the particle change direction? So again, if we follow this, okay, it's the particle, let's say we were kind of in the middle. The particle is at our left right now because it's negative and it's getting closer and closer and closer to us, but then it's going further and further away. It hasn't changed direction at all until it hits this point, right, which is when the velocity changes from positive to negative. So that makes sense because the velocity is talking about the direction of that it's going. So it's going in the positive direction, right, and then it goes in the negative direction during this whole point, and then in the positive. So the two places it changes are here and here, thinking about the velocity. So really easy to see with the velocity, a little harder to think about, but it does make sense with this. If it's going from left to right to us until it hits this point, then it's going right to left until it hits this point, and then left to right again. That's how we kind of look at that. When is the particle at rest? Again, when it changes directions at velocity equal to 0. So it's, again, it makes a lot of sense to look at the velocity curve there because it's just when it's equal to 0. Describe the velocity and speed of the particle. So it's pretty well described by this graph. When is the particle at point 5, 2? Well, I'm looking at this going 1, 2, 3, 4, 5. I don't think it'll hit. Oh, okay. So 5, 2 is talking about the y value being 2. So really it's just asking when does it hit a x value of 5. Well, remember that this graph here is in terms of t. And this graph here, even though it says y there, is really in terms of x because this was an x of t. When does it hit 5? I need to just count up 1, 2, 3, 4, 5. It's asking when does it hit 5 here. So when is the position at 5? So the position is at 5 at that point, and at that point. We have a particle at the point 5, 2. It's always at a height of 2 because it says the line y equals 2. So those would be those 3 points. Okay, so that's kind of our first look at particle motion. You can see how much easier it is to think about motion when you break it down from position to velocity. So let's look at a different rate of change. Let's just look at a volume and how it changes in terms of its radius. At what rate does the volume change with respect to the radius when r equals 2 feet? So we just want to find out, what is the rate of change of the volume in terms of the radius. So we just take the derivative of this. So we would say dV over dr is equal to, just use your power rule, 3 times 4/3 is just 4 pi r squared. So then we just plug in for r 2, so 4 pi times 2 squared equals 4 pi times 4, which is 16. Now, we got to think about units here. We're talking about volume. So this would be, one way of saying it, since it's volume, that's F, or feet cubed per foot, because you're saying how does the volume change with respect to itself. So you might just say that volume is really how does the, kind of like saying how is part of the area changing, because then it would be 16 feet squared, so it gives you an area dimension there. I'd probably leave it in the feet cubed per feet just to make sense of, we're asking how is the volume changing with respect to the radius. So keeping it in terms of a volume per radius length might help do that. By approximately how much does the volume increase when the radius changes from 2.2 or 2 to 2.2 feet? Well, simply we can just go, okay, it's V of 2.2 minus V of 2 all over 2.2 minus 2. So we do this, we've got 4/3 pi times 2.2 cubed minus 4/3 pi times 2 cubed all over 2.2 minus 2 is 0.2, which I get that to be 55.5. Approximately how much does the volume increase when the radius is changing? So that would again be in feet cubed per foot. Okay, so 55.5. May want to check my math on that, make sure I did that right, but I think that's all right. Okay, marginal cost is just asking how fast is the cost changing per whatever. Sometimes it's going to be per time, sometimes it's going to be per unit, depends on what you're given. So in this case, suppose that the dollar cost of producing X washing machines is C of X equals 2,000 plus 10X minus 0.1X squared. So this is in terms of every washing machine produced, this is the cost function. So find the average cost of producing 100 washing machines. So it would just be C of 100 all over 100, which equals 11,000 divided by 100, which equals 110. Let's see, what would that be? Average cost. I would assume that's dollars per machine. Oh yeah, there it is, because it's dollars. So $110 per machine. Okay, find the marginal cost when 100 machines are produced. So now we need to just take the derivative of this function. So the 2,000 goes away. So C prime of X equals 100 minus 0.1. Oh, sorry, multiply that by 2. 0.2x. Okay, so I'm trying to find that with 100 in here. So C prime of 100 is equal to 100 minus 0.2 times 100. That would be 20. So 100 minus 20. This is equal to 80. And again, that's dollars per machine. So that is the marginal cost when 100 machines are produced. What this tells us right now is that even though the average cost is $110 per machine, our instantaneous cost per machine, right now that we've produced enough machines, we're running at a lower cost per machine to produce these. So it kind of became more efficient the more we sold. But you can tell if the average was $110 per machine, that it must be higher earlier in the process before we hit 100 for us to be down at an instantaneous cost of $80 per machine now. So C says show that the marginal cost when 100 washing machines are produced is approximately the cost of producing one more washing machine after the first 100 have been made by calculating the latter cost directly. So it's just wanting to know what is the actual cost of this. So we would have to do, what is C of 101? So we're making one more minus the cost of 100. So this is total cost. So if we want to find out what the 101st machine would cost, we have to take the 101st total minus the 100 total and find it. And when you plug those in, you get about $79.90. So that would be showing that producing one more pretty much matches the cost. The marginal cost pretty much matches the actual cost of producing one more of these. Okay, so marginal revenue now. Suppose the weekly revenue in dollars from selling X custom-made office desks is R equals 2,000 times 1 minus 1 over X plus 1. Draw the graph of R. What values of X make sense in this problem situation? Just thinking realistically, we know you can't sell a negative number of desks, so we're definitely looking at numbers greater than 0. And just a good guess of kind of what this graph would look like. Probably you're not going to sell maybe more than like 100 or 200 of these, so maybe you just look at it. What does it look like from 0 to 100 or 0 to 200 as you graph it? So if we are just to put that into our calculator, the graph looks like this. If I was to draw it pretty quick, if that's 100, that's 2,000. Our graph kind of looks like this, and it gets closer and closer to that 2,000 as you get bigger and bigger in the numbers. So find the marginal revenue for when X desks are sold. So we need to take the derivative here. So this is a harder derivative. Let's see if we can simplify it a little bit. If we change this to, we're trying to find R prime of X. Okay, we can take the derivative, kind of ignore that 2,000, just leave the 2,000 out there. 2,000 times the derivative of the inside there. Well, the derivative of 1 goes away, so really we're just taking the derivative of this, which would be a negative parentheses X plus 1 to the negative first power. Okay, so that might make it a little bit easier. So let's just focus on taking the derivative of this here. So this negative would come out in front, so we go this equals a positive, and I'm just doing the middle. I'm going to leave that 2,000 low right now. So it would just be a positive x plus 1, right, and then the power has to go down to negative 2. So using the power rule, so I can stick that 2,000 back in front here. So that would be, if we did dx to that parentheses there. Okay, so taking that derivative, that gives us that. Really, when you do this, this is called the chain rule, and we haven't really gotten to it, but the derivative of the outside, leave the inside alone, take the derivative of the inside is how you think of it. The derivative of the inside is just 1 though, so it's not going to change it. So it works this time. So this would be our marginal revenue when X desks are sold. You'd probably see it written closer to R prime of X is equal to 2,000 over X plus 1 squared. That's probably closer to how you'd see it. Now use this function to estimate the increase in revenue that will result from increasing sales from 5 desks a week to 6 desks a week. So what we're really asking here is, what is R prime of 5? What is it? How is this changing at 5 when we change to 6? So it's just 2,000 divided by 5 plus 1. There's that changing by 1. And that's equal to 55.56, I think, dollars as you increase from 5 weeks to 6 weeks. Okay, well, I know that these word problems are hard and a little bit confusing. If you can just simplify them to, they are rates of change. How is whatever we're talking about, whether it's position changing in terms of time, that would just be velocity. How is velocity changing in terms of time? That would be acceleration. How is a volume of something changing per maybe radius or per some other length? So we're really just taking derivatives. So it's adding a bunch of words to try to be able to understand derivatives in a more meaningful, more useful, real-world way versus just kind of abstract mathematically. This is hard, so we'll have less problems to work on, but they will be all word problems this section. So bring in questions that you have in class, and we'll see how we do. Thank you very much. Bye.